Hey, this is Steven from LegitTechTutorials, and we are back in our product design series working on the automatic spooler and the dimensional control modules. So last tutorial we did these adjustment screws, and now we're going to continue doing our desired cleanup. So we're going to spend another 30 minutes doing some basic cleanup. And we are going to make sure that everything's looking good. As we saw with that other, on the last setup, we had the issue of the we had some things that were kind of broken, so we're going to fix that and do what we need to do here. Alright, well, right now what we need to do is we need to add this distance from there to there. From there to there. It's 0.301. So I need to add 0.301. I don't know why it's 0.1. That's probably because something's skewed out. 1.506. 1.426. 1.426. And then the other issue is this bad boy here. Need to get rid of that line. And just go all the way out. Alright. Wait, what? This has got some weird stuff going on. Anyways, alright, so 1.46. This guy's got to be, I'm going to assume it's going to be the same as that, 1.1225. And then what I'm going to need to do is I'm going to need to dimension this guy being parallel to that guy. This guy always being parallel to that guy. Alright. So now this guy is a specific distance from that guy. .125. I should probably add a 1/4 of an inch there. Let me look at my calipers. 0.20 is fine. So let's, what did it have? 0.20, so let's make this 0.46. Okay. Now we should be looking good. Oh. Which one was this one? Yep. Alright, that is looking good. Why is it not? I mean, not like it could go that far anyways, so that's pretty much as far as we want to go. This is going to be really sweet, because now if I print it this other way, print it flat. Oh, so now we have another issue with printing flat, this thing being like that. This guy's going to have to be printed this way somehow, some way. I'll figure that out. As right now, this guy is aesthetically good. Can't really be solved very easily. As far as printing with these slots here. Only thing I could think of is if this came to like a point, but then it's still floating over here. Maybe if this guy was like a diamond somehow. I don't know. We'll figure it out. Alright, we're at 50 minutes. So let's go back and change this bad boy here. And figure out what's going on here. Alright. What happened? What happened? Okay. I'll just force these parallel. Oops. And that's probably 1 inch. Nice, good. Something getting all wonky. But it's a circle. Doesn't really matter. Wow. How does it do that? There we go. And there she goes. This also is going to need to have that little square on it. So let me go ahead and go back to this one and then figure out that little offset. Whoa. Ah, this guy. Okay. What? That is the weirdest thing. Never seen that happen before. .35. Okay. did I say 0.35? So it's 0.175. And then maybe I could just set this as 1 dimension. And then set these both to be parallel. And then I can draw a square off of that. 0.35. Draw from there to there. All right. And then yeah, so this is going to be, it really depends on which side you make the top. It's arbitrary. Symmetrical amount about around the right hand side or whichever axis they want this to be. Alright, so it's 0.35. Really need to start naming these. .75. This guy, on the other hand, it's 0.35. This is like 0.75 or something. Alright, stop sketch. Edit feature. Don't do that one. There you go. The interlink 402 will fit right in there. We're at 13 minutes. Everything is looking good. Whoa. I didn't know that. Whatever. It's kind of cool. How did I do that? I just held it. I just held on this the rotation cube. Alright, that looks good. That looks good. What I'm gonna do, since we have some time, maybe this video will actually be 30 minutes, is let's turn this guy into a circle up here finally. Circle, center diameter circle. The motor, I don't even know where mine was. I was gonna take a guesstimate as far as my calipers on how thick it was. It's about like 1.3 inches in diameter. Alright. So there's that guy. And it's going to make it the same on the other side. Can that be printed? It's an overhang there. There's definitely a lot of challenging pieces on this project. This other one over here, so this, I definitely don't want to extrude like the other side. Let's do, so what do I want to do? Sketch, showing the other side. Okay. Turn those off. Because it could do this, no problem. This, on the other hand, may or may not be able to do. And as you see, this weight, man, is going to put a lot of moment on this. We'll see if we have anything else, and then I'm going to test this and see, like, what type of strain are we talking about here. I've been doing some simulation stuff on some of my other videos, so maybe if we have enough time, we'll check out that and see if this is even feasible here. This is good. This is okay. These are a little small on the spring size. These are okay. This one I just checked. That's okay. That's okay. That one needs some work. This one's okay. Why I say this one needs some work is what was the spring size on this bad boy here? This was a 1/4 inch. And this one, oh, this was 1/4 inch. I'm perfectly cool with 1/4 inch. 1/4 inch spring is fine. It's a really small spring. But we'll get a really nice small spring. Okay, well this one's okay, this one's okay. So yeah, let's maybe do a quick simulation on this guy. So what we're gonna do is we're going to do a simulation, push it to simulation, and we're gonna do a new static stress study. And then basically what you do here is you add a constraint, like which surfaces are fixed. And so what we're going to do is we're going to make all these inside faces here fixed so they don't move on X, Y, and Z. And then what we're going to do is we're going to put a force either on the top or on the inside face of this guy. So what I'll do is I'll put a force here down, and this will be, let's do it in kilograms, or well, this one's newtons, mass is in kilograms. It's just US pound mass, S force is pound force. So just do weight, which is a force. So here, one side's, so let's just say that this guy here, the motor on that, weighs half a pound. So we have 2.2 pounds is the kilogram. So let's say 2.5 pounds for the entire spool plus another 0.5 pounds. And the cones are negligible. So let's just say 3 pounds total. So let's just say 1.5 pounds on this side. And then 1.5 pounds on the other side. Wait, what? 1.5. Oh, it's kind of like constraining them, but you know they're in there. 1.5 and 1.5, and they are in the right orientation. So let's go ahead and look at what material should be. ABS. Obviously with ABS, we have a little bit more ductility, not as much strength. So we're just going to go on yield. I don't know what else PLA is similar to. I don't know 100% about it, but we know that it's similar. Solve on local machine. And then what we're going to look at is we're going to look at the factor of safety and then maybe some stresses. And the stresses are going to be in Stresses that are in PSI. Whoa. Okay, so what you're looking at, check it out. You can see the distortion. That's really cool. So what you're looking at right now is like a adjusted. So this is just to show you what it would look like when it deforms. And then here's adjusted 5 times. So that's what it's trying to do. So as we're looking at it, we could tell that, okay, this is what we would expect to happen. Interesting. It has a little bit extra scale on that. I don't know why that is. Why is that? They're identical on both sides. I don't know why this is like that. Anyways, maybe because it has more. Maybe because it thinks it has more material in there. Who knows? So what we're gonna do is look at. We're gonna look at not undeformed, but actual. So we're gonna go to actual. Oh, we have a little bit of deformation. You can see that it's, you know, approximating our shape with that many polygons, but that's fine. It's not our exact shape, but it looks good. So what about on this side? This side's going to probably have a little bit of deformation also. A little bit of deformation, starting to fold. What about down here? Like very little deformation. Interesting. So in PLA, it's stronger, so you're not going to have as much deformation, but you're going to be getting close to failure. So here, deformation scale, what we're going to do is show min and max. The min is right here at the folding, is right here at this point. It's 13.2. So 13.2, and then what we can look at is we can look at the stress. This is in von Miss, PSI, or we can look at megapascals, blah, blah, blah. So here's a PSI. We could see here, if we go, as you can see, this program is amazing. So we could go up here, and then we could look at where all the stresses are. So here, like, not too much, not too much. It's starting to go to minimum. Minimum's up here. And then a lot of stress is starting to load right here. So here's where all our stresses are. This is actually keeping a lot of taking all of the brunt of these two, connecting these two together. It's kind of interesting. And then here is doing pretty good to distribute the load. So most of our forces, as you would think, is right here. I don't know why I guess it's that small mass is what makes it think that it's going to do more here. So that's what we got. And then our max is a red area, which there is none, which is like very small. Probably the red is so even minuscule. It's in, I think it's in the bottom side. Oh, yep, there it is. It's in the bottom side. So that's where our max stress is right here. So if it's going to break, it's going to break right here. But you can see at least that this is starting to discolor, which means that we are starting to absorb some force here. Because if you go up here, you will see that there are a little bit of forces distributed on this piece. And then this is another force that we have to look at is we're looking at some tension here. So maybe we'll add another force. Force right here in the center. And then that one goes up to 22 pounds. The FSR. So let's just say that we're doing, I can't remember where it was linear again. I was researching it, the FSR, to figure out where we could use Hooke's law, F equals kx. So that was, I think, somewhere in the at least 3 pounds minimum force range. So let's go ahead and put that, and then we'll resolve it and see what happens here. So that's the pulley. The pulley is going to be pushing it up with that much force because the pulley is going down here, and then as it comes, the motor is going to be pulling tension on this guy and pushing up at that point. So if it's pushing up at that point, it has to also be doing something over here. So we would have to add that 3 pounds over here on this side. If I'm thinking about, I'm doing this pretty quick, so I'm not giving myself any chances to really think about it too much, but it's pulling, this needs to take the rigidity of it pulling here. So let's add the extra force here. we go. Alright, so we got a little bit more deformation here. And we're back in the realistic deformation scale, actual deformation scale. So let's go ahead and look at the displacement here. Alright, so the total is this guy is going to go down 0.06 of an inch. 0.07. So let's take a look at that. 0.07. How much is that? And of course, this is ABS. The PLA is not going to move. PLA has a lot more strength, but very little ductility. So it's gonna snap before it. Oh, look there, it's got almost nothing there. So this is like 0.015 of an inch. So that is 15 thousandths of an inch. Here is 67 thousandths. So that's a pretty small number. All right. So anything else here? I'll do one more thing. I'll just see what it takes to make this guy fail. And I could be off on this. I always get confused. The worst thing about in my engineering programs is the forces. It's really confusing because they just keep moving around the metrics. So they tell you what a scale weighs. In your scale, it doesn't say you weigh 50 pounds force, but is the scale contributing? Is it taken away from is it measuring your mass or your weight? That is the difficult thing to measure. Actually, let me look that up right now, because I always need to look it up because the classes are really confusing. Okay. Okay, here it's saying it weighs force. This one is contradicting itself. Yeah, I mean, it would be a lot more helpful if it told you, hey, well, I'm measuring, mass instead of force, because you have pound mass, pound force. Typical bathroom scale measures force, your weight. Okay, so yeah, so a kilogram spool weighs 2.2 pounds. So I mean that's not a lot, I'll tell you that. So what I'll do, because I really want to have some fun with this, is see where it fails. So let's do like real high. And this other force there, we don't want that force there, so what did I just put on this one? 20 pounds. I really want to see this guy break. Or yield. I want it to yield. So what I'm going to do is solve it. And then this will be the last thing I'm going to do with this guy here. So I was just curious to see if this guy would break. So now that we know it's not going to break, we're good to print it. It'll definitely hold for 2.2 pounds. But of course you have to multiply it by, some sort of oh, yep, it's yielded at that point. It broke at that point. So yeah, when it says safety factor is a 1, safety factor is, let me make sure I get this right. Safety factor is your yield, or it depends on what you set it as. So here I could set it as my yield strength or ultimate tensile strength, right? Ultimate tensile strength is at the peak, at the top peak. I should have showed you guys some results before I talked about this, but what like plastic looks like. Plastic yields a lot. So plastic, like if you have a graph where it's just stress here, sorry, this is strain, this is stress. Stress is force over area, and strain is delta L, or the change in length over the original length. So that is a unitless value. It should be that. I could be off. I forget all the time. So if here is your graph, here in this corner, plastic goes like this, and then it hits a yield point, and then it has like a little up and then a down. So this yield point here, the yield point is, sorry, the ultimate tensile strength is the max part of the curve, and the yield strength is where it goes from a linear line to a curved line. And the curved line is in plastic deformation, so that means if you loaded something and you go into plastic deformation and you let it go, it won't return back to its original size. It is permanently deformed to that shape. If you're in that linear area, it will snap back. So that is just a. I'll go over it again in another video. So again, if I go from here, display and results view. 1.5 means that it's a safety factor, which means that it's the applied stress. It's the yield stress over the applied stress. So what that means is that they're equal. 1 means that what's above is equal to what's below, and that means that at this point it's going to yield. It's almost going to yield. It's at 0.05. So it's about to give up, and then it will deform, and then it will always be stuck in this shape. And then any further loading past that point, it's stuck in that shape, stuck in the new shape permanently. You can see how much it's deformed here. And so PLA will not take that. It will not take this load. If it bends that much, it's going to snap, because PLA is very brittle. It's very strong, so basically the difference, if we go back to the graph again, the difference is the strength, or the Young's modulus, which is basically the slope of the starting line. So ABS could be here, right? It's like a very low acute angle as far as slope, right here, but PLA could be like up here. It could have a big slope, but it doesn't yield as far. So ABS stretches more before complete failure and snaps, and PLA does not stretch as far. Another thing is that PLA will go into plastic deformation with less stretching or less strain than ABS. ABS will go further. So the higher up you have of your slope, usually the earlier it goes into plastic deformation. But if you have a slope like that, then it's going to go into plastic deformation later on in the strain. But unfortunately, I couldn't find any mechanical properties for PLA in here. Oh, and we notice that, oh, no, it's still in line here. Okay, because we don't have any tangential stuff going on. So one last thing that we're going to look at here, which is our displacement. We're looking at almost ½ an inch. It was ½ an inch down. It's a lot. Before it starts to go into plastic deformation. And then I'll do one last thing, which is I'll do it for its ultimate tensile strength. And then pretty much after the ultimate tensile strength, it's pretty much done. So let's just see. Oh, we're already solved. Okay, so I guess it just 1.35. So it would take just a little bit more before it gives and just blows up. Probably within 4 pounds or so. Yep, so it's about to blow at probably 25 pounds. So that's a total of 50 pounds. So this guy could hold 50 pounds in ABS before it snaps, and he could hold 40 pounds before it starts to deform. So, and that's with ABS. So with PLA, it depends. I'll have to look at the different graphs and stuff. And they're Young's modulus mainly, because we're talking about we want to design in that straight line. We don't want to design in the plastic area, because once you have plastic area, it deforms and shit goes out of whack. We want this form to stay. You want this form to stay like this, not like this. But people are now designing stuff where the whole machine will operate in this stress state, because you get a lot more force and a lot more deformation before stuff breaks, and then you could work around the ultimate tensile strength. Alright, so yeah, I'll have to look at their Young's modulus, because we're working in the slope range, not the curved range. Because the slope range, it'll pop back to shape. So we need to compare in that. And as far as that's concerned, the higher the slope, the higher the Young's modulus, which means the stronger the material is, but the less ductile the materials. And the line with the less slope has a smaller Young's modulus, but generally is more ductile. Alright, that is pretty much it for this video. I don't know how long I've been going on, 104. I had to close, 38 minutes. Yep, simply close it. Alright, so this has been Steven from LegitTechTutorials. I'd like to thank you guys for watching. If you like this video, please subscribe for more videos like it, in this series and other series as well. I will talk to you guys later. Thanks for watching. Take it easy. Peace.